Let us see few numericals from kinetic theory of gases and radiation. The first question is calculate the ratio of the mean square speeds of molecules of a gas at 30 Kelvin and 120 Kelvin. So we have been given two temperatures. One is 30 Kelvin, other one is 120 Kelvin. And we need to compare the ratio, or we need to compare the mean square speeds of the molecule. That is RMS speed. RMS speed is root mean square speed of the molecule. So we know that RMS speed is directly proportional to square root of temperature. Is directly proportional to square root of temperature. So using this formula, since there are two temperatures, I will say the first temperature as T1, that is given as 30 Kelvin, and second temperature as T2, that is given as a 120 Kelvin. So when I compare both the RMS speeds, I can write speed C1 upon C2 will be equal to root T1 upon T2. So since I need to take the ratio, I will be writing this as root 30 upon 120, and this will be equal to square root of 1 by 4. 34 is 120. So square root of 1 by 4 will be 1 by 2. So the comparison of the two speeds will be 1:2. There are two vessels A and B which are filled with the same gas. Now in the question they've already mentioned the vessels are filled with same gas where the volume, temperature and pressure. There are three quantities which are given. One is given as volume, temperature and pressure in vessel A is twice the volume, temperature, pressure in vessel B. So this is the given data which is given to you. The pressure, the volume, temperature and pressure in vessel A. So let us say let PA, VA, TA be the pressure, volume, temperature of A. And similarly, since there are two vessels, so let PB, VB and TB be the pressure, volume and temperature of B. Pressure, volume and temperature of B. So there are these three things given to you: pressure, volume and temperature. PA, VA, TA for vessel A, PB, VB, TB for vessel B. We need to calculate the ratio of number of molecules of the gas in vessel A to vessel B. Number of molecules means Na upon Nb. We are supposed to compare. Now we know that the ideal gas equation, PV equal to nRT, and I can write PV equal to, in terms of number of molecules, I can write N upon Na, that is Avogadro number, into RT. We have learned this, that the PV equal to nRT can be replaced by PV equal to N. Capital N is number of molecules, Na is Avogadro number, small n is number of moles. There are three things that we should make clear. Small n is number of moles, okay, but we are being asked number of molecules. So number of molecules, there is a formula for number of molecules, number of moles equal to number of molecules upon Avogadro number. Here there is a reason, N equal to N upon Na. Small n is number of moles, capital N is number of molecules, Na is Avogadro number. So if I write it for two cases, I can write PAVA equal to Na upon Na is the Avogadro number into RT. The denominator is Avogadro number. And similarly, I can write PBVB equal to NB upon Na into RTB. Here also I will write it as RTA. Now, in the given data, what they have been given to us, as I have mentioned already, they are telling that this line is very important. The volume, temperature, and pressure in vessel A is twice that of volume, temperature, pressure in B. So they have given PA is 2 times of PB, VA is 2 times of VB, and TA is 2 times of TB. This is given to us. Pressure, temperature, volume in vessel A is means equal to, twice means 2 times that of B. So PA equal to 2 PB, VA equal to 2 VB, TA equal to 2 TB. So let us divide these two equations. So on dividing the two equations, we get PA VA upon PB VB equal to, this terms will get cancelled. R and Avogadro number, when you divide, LHS may divide hoga, RHS will be divided in RHS term, and when you divide, you see R and Na, that is Avogadro number, and R will get constant. So here you are only left out with Na upon Nb into Ta upon Tb. Just substitute the value. So on substituting the value, you can write this 2Pb into 2Vb and keep denominator as it is. So this is 2Tb upon Tb. So Tb cancelled, Vb cancelled, Pb cancelled. 2 also cancelled. So what are we left with? Na upon Nb is equal to 2. So therefore Na upon Nb is just equal to 2 upon 1, that is 2. So the ratio of number of molecules is 2:1. Next, a gas in a cylinder is at pressure P. They have given the gas is having in a cylinder which is having a pressure P. If the masses of all the molecules are made 1/3 of their original value. So let small m be the mass of the molecules. Let small m is mass of molecules. So they have been becoming 1/3 of their original value. So I can say m dash is 1/3 of the original value, say m, and their speeds are doubled. So say c dash equal to 2 times of c. C is the speed. Okay? RMS speed. We usually take it as a RMS speed. C RMS. So c dash in textbook they have denoted c RMS or v RMS, whatever it is, fine. You can denote velocity with c or v. Even c is fine. So C dash RMS equal to 2 C RMS. This is given to us. Find the resultant pressure. A pressure in a cylinder, a gas in a cylinder is at a pressure P. So we know that pressure equal to 1/3 rho C square RMS. We have this formula. We have derived this relation. Rho is the density. So I can write pressure P equal to 1/3. Density is mass upon volume. And mass is number of molecules into mass of each molecule upon volume into C square RMS. So the bracket term which I have written, Nm upon V, is the density of the gas. This is the formula for density of the gas. Density of gas rho is equal to Nm upon V. Capital N is number of molecules, small m is mass of each gas molecule, V is the volume. So I can write similarly for other case also. So I can give this as equation 1. I can write another case, the resultant pressure. The second pressure is what I'm supposed to find. So I can write it as P dash equal to 1/3 N M dash upon V C dash square RMS. Divide 1 and 2. When you divide 1 and 2, what do you get? P upon P dash equal to, if you see 1/3 NV will get cancelled. 1/3 NV will get cancelled. Here you have left out with the M C square RMS. And here you are left out with m dash c dash square RMS. Now let us just substitute the value. Keep the numerator term as it is. Let us substitute the denominator term, m dash and c dash. The values we have been known. So I can put this as 1/3 m, and this I can put 2 into c RMS. But here it is already c dash RMS square. So इसका square करके डालेंगे. So that will be 4c square RMS. Please make sure that here the value is a squared value. It is not directly 2 RMS, 2 CRMS नहीं put करना है. Square करके I have substitute the value. So if you see this again gets cancelled. So I'm left out with P upon P dash equal to 1 upon 1/3 and 4. So this is 4/3. In the denominator में 4/3 है. ठीक है, 1/3 into 4 ना. This 1/3 into 4 in the denominator only. So ये ऊपर जाएगा तो it will become reciprocal 3/4. So what is the new pressure? The new pressure P dash is 4P upon 3. That is our answer. Next question, show that the RMS velocity of an oxygen molecule is root 2 times that of a sulfur dioxide molecule at SCP. Now this is very important thing. You have to prove that the RMS velocity of oxygen. So we have already seen CRMS is equal to root 3 RT upon molecular mass, M0. 3 is a number, R is universal gas constant, T is temperature, M0 is the molecular mass. There are two things given, oxygen molecule and sulfur dioxide molecule. When we talk about molecule, molecular mass of SO2, sulfur dioxide, SO2 ka molecular mass is 64. Please remember this value. The values are not given to you. It is supposed to be remembered by you. Molecular mass of oxygen, O2, will be equal to 32. So these values we should know. At least for this numerical, the SO2 is 64 and oxygen is 32. This is what we should know. This is for the molecule they have been given. So as far as units are concerned, they are gram per mole. Gram per mole. So we need to compare the RMS. So what do you see? You see that RMS velocity is inversely proportional to root of molecular mass, right? Because 3R and T is the same. 3R and T will be constant in both the cases. We just need to compare. So when you compare this, so suppose CRMS of SO2 divided by CRMS of oxygen will be equal to, उल्टा हो जाएगा, square root of m naught of oxygen divided by m naught of SO2. So I just need to compare the value, just substitute the value. Oxygen का value कितना है? Oxygen value is 32 upon 64. So this will be 1 by 2, so this will become 1 by root 2 inside the root. So CRMS SO2 divided by CRMS O2. Just cross multiply this. So what do you get? So CRMS O2 into 1, CRMS O2 हो जाएगा, will be equal to root 2 will get multiplied here. Root 2 times CRMS SO2. This is what they were supposed to prove. Na? This is what they were supposed to prove. Show that the RMS velocity of oxygen is root 2 times SO2. So oxygen is root 2 times SO2. At what temperature when the oxygen molecules have same RMS speed? The RMS speed in the question is saying they have a same RMS speed. At what temperature? Temperature is supposed to be found out. They have same RMS speed as that of helium molecules at STP. Now, please remember, students, STP is a very important thing to be remembered by you. Please remember, I will just use some different color. STP means standard temperature pressure. We all know it is standard temperature pressure. We should know the value. No one will ask you full form. You should know the value. What do you mean by STP? STP is 0 degrees Celsius, that is 273 Kelvin, and 1 atmosphere is equal to 1.013 into 10 raised to 5. In many chapters we have learned this value, 1 atmosphere value. So you need to remember, whenever STP is asked, STP means 0 degrees Celsius, 273 Kelvin, and 1 atmosphere, that is 1.013 into 10 raised to 5 Pascal. This is what known as STP. The question is asking, you have to suppose to compare the, you have to find the temperature. You are supposed to find the temperature, right? You are supposed to find the temperature. The oxygen molecules have same RPS speed as that of a helium. So again, molecular masses, okay, here they have provided the molecular masses. Oxygen ka 32 and it is 4 for helium. So molecular mass of oxygen is 32. This is given to you. Molecular mass of helium is 4. This is given to you. At what temperature? So again, since their RMS speed is same, so I can equate RMS speed of oxygen equal to CRMS of helium. I can equate both, and I'll use the formula root 3 RT of oxygen upon molecular mass of oxygen equal to root 3 RT of helium upon molecular mass of helium. So I can see the 3R will get cancelled. Root also will get cancelled. I'm just left out the T of oxygen upon molecular mass of oxygen equal to temperature of helium upon molecular mass of helium. So just put the values which are given to us. Helium, for helium they have been given, helium ke liye they have been given the temperature is 273 Kelvin. We are supposed to find for oxygen. So TO upon molecular mass of oxygen is 32 equal to temperature for helium will be 273. Here the number which I have told you, STP, divided by molecular mass of helium is 4. So just solve this. Temperature for oxygen will be 273 into 32 divided by 4. So when you solve this, you get the temperature for oxygen as 2185, nearly 2185 Kelvin will be the answer. Compare the RMS speed. Again, one more numerical on RMS speed. So you can see RMS velocity is very important topic. We should keep on practicing that formula. The RMS speed of hydrogen, oxygen, of hydrogen molecules at 127 degrees Celsius. Now already they have given one temperature. Temperature for hydrogen is given 127 degrees Celsius. Speed converted to Kelvin. So 273 plus 127. This will be 400 Kelvin. Similarly, for oxygen is given. Temperature for oxygen is given as 27 degrees Celsius. 27 plus 273, this will be 300 Kelvin. You are supposed to compare what? Compare the RMS speed. As I told you, RMS speed means CRMS of, पहले क्या दिया है? पहले हाइड्रोजन दिया है, बाद में ऑक्सीजन आया है, तो लाइकवाइज कंपेयर हाइड्रोजन ऑफ, comparison of hydrogen with oxygen. This ratio you are supposed to find. Molecular masses are given to you. Molecular masses are given to you. Molecular masses of oxygen, molecular masses of hydrogen is given to you. Molecular mass of oxygen is 32. This is 2. So I hope you know the formula what you are supposed to use. The same formula, CRMS of hydrogen upon CRMS of oxygen will be equal to, I will make one common root. and 3RT first hydrogen है, so 3RT hydrogen, molecular mass of hydrogen. In denominator that is oxygen, I will reverse that. I'm avoiding one step over here. No need to write that. I hope you all understand this, what I have done. 3RT of oxygen. Okay, I've just reversed the denominator. I have reversed the denominator in the under root. 3R cancel. Just substitute the value. Temperature of hydrogen is 400 divided by molecular mass of hydrogen is 2 multiplied by molecular mass of oxygen is 32 divided by temperature is 300. So we can just simply first cancel out these zeros. We can first simply cancel out these 2. 2 into 32 is root 64 upon 3. Root 64 is 8. So 8 upon root 3 will be your answer. 8 upon root 3 will be your answer. Since they have told to compare, so you will just keep it in ratio. Whenever there is compare as, you just keep it in ratio. No need to put the value for root 3 and so on. Find the kinetic energy of 5 liters of a gas as STP. Again, STP is asked. STP means you should know that pressure will be how much? 1.013 into 10 raised to 5 Pascal. 5 liters of gas. Please remember, liter is a CGS unit. Volume is given 5 liters. Convert liter to meter cube. So you multiply by 10 raised to minus 3. Convert liter to meter cube. You multiply it by 10 to the power minus 3. You are supposed to find the kinetic energy. Okay, here the standard pressure is given. Okay. So kinetic energy, when you have been given pressure and volume, generally students know kinetic energy formula is half mv square. But here there is nothing called as half, there is nothing m, mass is not given, there is nothing velocity is given. So you will not use half mv square, you will use in terms of pressure and volume. So in terms of pressure and volume, the kinetic energy is 3 by 2 PV. This is a very important formula, one should know. Kinetic energy is 3 by 2 PV when pressure and volume are given. So everything is given to you. 3 by 2 into 1.013 into 10 raised to 5 into 5 into 10 raised to minus 3. So just solve this answer and you will get the final answer for this. So this will be 759, 759.7 joule. 759.7 joule will be your answer. Next. Calculate the average molecular energy per mole. Okay, now there are three things given. Average molecular energy per kilomole. So first formula, average molecular kinetic energy per kilomole. The formula for this will be 3 by 2 RT. So 3 by 2 RT. R is given to you. Yeah, R is given as 8.31. So just take that value. Actually, R value is 8.314. The actual value which you have learned in from your textbook is 8.314. And in the numerical, they have given 8.31. Just take that only. 8.31. 8.31 into temperature. Temperature they have given as temperature they have given as 127 degrees Celsius. Yeah, they have given the temperature 127 degrees Celsius. You convert that to Kelvin, that will be 400 Kelvin. I have done it back here. We have converted that, so you can see here how to convert. That is 400 Kelvin. So you solve this, you get the answer over here. You get the answer as 4988 joule merely. Second point, they're asking find the kinetic energy per kg, kinetic energy per kilogram. Kinetic energy per kilogram. For that case, the formula is whatever you have solved above divided by molecular mass. So kinetic energy per kilomole divided by molecular mass. This is the formula. So 4988 divided by molecular mass is given. Yeah, they have given 32. So 4988 divided by 32. This will be 155.8. This will be joule. 155.8. Next, kinetic energy per kilomole per molecule. Sorry, kinetic energy per molecule. Per molecule means divided by Avogadro number. Okay, so this will be simply 3 by 2 RT divided by Avogadro number Na. So this will be 4988 divided by Avogadro number is given to you 6.022 into 10 raised to 23. So when you solve this, 8.28 into 10 raised to minus 21 joule will be your answer. So these are the three relations: molecular kinetic energy per kilomole, kinetic energy per kg, kinetic energy per molecule. So the formula need to be remembered. Calculate the energy radiated in 1 minute. Energy radiated in 1 minute you are supposed to find. So time is given to you. 1 minute means 60 seconds. Now somewhat we are going to solve for radiation part. I guess kinetic theory is completed. Now we will see for radiation part. Calculate the energy means heat energy. Q you are supposed to find. Time is given to you. Surface area is given to you 100 centimeter square. Convert it to meter square, and temperature is given to you 227 degrees Celsius. 227 plus 273 will be 500 Kelvin. So we know sigma value is also given to us. That is a constant. So we know this value Q by T equal to sigma A T raised to 4. We know this particular relation. So therefore Q will be equal to sigma T A T raised to 4. So just put the value. Just substitute the value for sigma T, capital T, area, everything. When you substitute the value and you solve, you get the answer as 2126.2. This is your answer. Joule. So Q equal to sigma T A T raised to 4. So substitute the value, you will get this answer. Energy is emitted from a hole in an electric furnace at a rate of 20 watt. So at the rate of 20 watt, watt means, you always remember power का unit होता है watt, and power is energy upon time. Energy upon time means Q upon T. Energy is Q, time is T. That means Q upon T value is given to you. That is Q upon T is 20. They have already directly given Q upon T. Okay, you are not separately solving Q upon T. Directly they have given Q upon T value. Temperature is given 727 degrees Celsius. So 727 plus 120, sorry, 273. When you do, this will be 1000 Kelvin, right? Then they have been given what is the area of the hole. Area you are supposed to find. When the sigma is given, Stephen's constant value is given. So whatever value is given, just take that only. Sigma equal to 5.7. Although it's a constant value, sometimes they change, sometimes they just keep some other value to make calculation easier. Joule per second, meter square, Kelvin is same formula, the back B's which we have used. Q by T equal to sigma T raised to 4. Okay, A sigma T raised to 4. So I need to find A. So A will be equal to Q upon T divided by sigma T raised to 4. So Q upon T is 20. Sigma value is 5.7 into 10 raised to minus 8. T raised to 4, 1000 raised to 4. So 1000 I can write 10 raised to 3, 10 raised to 3 raised to 4. So 10 raised to 3 raised to 4 is 10 to the power 12. See, whenever you have 0, just make it to 10 power. So it is simple to solve. So 1000 I can write 10 raised to 3 and write 10 raised to 3 raised to 4 as 10 raised to 12. So everything will be solved in 10 to the power 12. And when you solve this, you get the area as 3.5 into 10 raised to minus 4 meters square. This will be your final answer. 3.508 something will be your answer, to be very specific. Emissive power of a sphere of area is given. Area is given as 0.02 meter square. Emissive power is 0.5 kilocalories per second meter square. So this is, they have already given. Q upon AT is given to you. Emissive power Q upon AT. This is Q upon AT value which is given to you per second meter square. What is the amount of heat radiated by the spherical surface in 20 seconds? Time they have given 20 seconds. What is the amount of heat which is radiated in time 20 seconds? So you will use the same relation. Here actually we will use calories, since they have given in calories. So it is fine if we keep it in kilocalories or calories only. The textbook has kept the answer in calories itself. It's okay if we also keep, or if you want, you can convert it to SI unit. It is okay. It is surely fine. This is the radiant power. Emissive power means radiant power they have given. R is the radiant power which is given to you. Q upon AT. So what is the amount of heat radiated by the spherical surface in 20 seconds? They are asking. What will be the amount which is radiated in 20 seconds? That is heat. What is the amount of heat means Q? Heat means Q is been asked. So from this relation only, we'll use this relation. R equal to Q upon AT. So Q is equal to R into A into T. So Q will be equal to R value is this 0.5 kilocalorie. Let us keep it in kilocalorie only. Into area is 0.02. I can write this 2 into 10 raised to minus 2 meter square. Into time is 20. So when you solve this, you get 20 into 10 raised to minus 2 kilocalories. That is your answer. That is 0.2 kilocalories. So this is the formula. Actually, I've written the formula here only. This is the formula that you are using here. And Q is been given. Q you are supposed to find. R, A, and T is given. Compare the rates of emission. This is a very, 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 very important question, children. This is a very important previous year question. Many times it has been asked in board exam. Although the numbers are changed, but many times like this we have solved example also. So the solved example is also asked in board exam. So both sums are important. One we have it in exercise, one we have in solved example. So both are important. Please make sure you practice these types of sums and please go for a board exam. This is very important question. Compare the rates of emission. Rates of emission means, say, let us say R1 and R2 are the rates of emission of a black body maintained at 727 and 227. So suppose first temperature is 727 degrees Celsius. Second temperature is 127, sorry, 227 degrees Celsius. So you add with the 273, you get here 1000. You add here 273, you get 500. So these are T1 and T2, and the surrounding temperature is 27 degrees Celsius. Surrounding temperature is T naught, that is 27. To convert that, 300 Kelvin. So we know that from Stephens-Boltzmann law, using Stephens-Boltzmann law, R is equal to sigma T raised to 4. And when there is a surrounding temperature, so T minus T naught raised to 4. This is the formula. Since surrounding temperature is given to us in our question, so this will be sigma T raised to 4 minus T naught raised to 4. So since there are two things, I will write R upon R1 upon R2 equal to sigma 1 upon sigma 2. Sorry, not sigma 1. Sigma is a constant. So this will be just sigma. This will be sigma T1 raised to 4 minus T naught raised to 4 upon sigma T2 raised to 4 minus T naught raised to 4. Sigma getting cancelled. T1 raised to 4 is 1000 raised to 4. 1000 raised to 4 minus 300 raised to 4 divided by 500 raised to 4 minus 300 raised to 4. So when you solve this, you get the answer nearly 18.23. 18.23 is your answer when you solve this. The Earth's mean temperature can be assumed to be 280 Kelvin. How will be the curve of a black body radiation look like for this temperature? Find out the lambda maximum in which part of the electromagnetic spectrum does this value lie. Now we know that lambda max equal to V by T. Wien's displacement law. From here we have known this formula. Lambda max is what I'm supposed to find. Temperature is given as 280 Kelvin. Wien's constant is given to you in the question. V equal to 2.89 into 10 raised to minus 3. So lambda will be equal to 2.89 into 10 raised to minus 3 upon 280. So when you solve this, you get 1.035 into 10 raised to minus 5 meter. And in which spectrum does this electromagnetic spectrum does it lie? It lies in the microwave region. It lies in microwave region. You are supposed to at least remember the range of each region. Electromagnetic spectrum consists of 7 waves: radio waves, gamma waves, X-rays, UV, visible, infrared. These all rays, you have to know the range in which the wavelength lies. So this value which we have got 1.035 to 10 raised minus 5, this lies in the microwave region. A small blackened solid sphere of radius is given 2.5 centimeter. R is given to you 2.5 centimeter. Converted to meter. This is given to you and is placed in an evacuated chamber. The temperature is maintained at 100 degrees Celsius. So they have been given temperature 100 degrees Celsius converted to Kelvin. So this will be 373 Kelvin. At what rate must energy be supplied to the copper sphere? At what rate? Q by T. Energy supplied Q by T. At what rate? Rate means divided by time. What divided by time? Energy divided by time. And as I told you, energy divided by time is power, right? Q by T is power. Another temperature is given as 110 degrees Celsius. There are two temperatures given. One is given as 100, one is given as 110 degrees Celsius. There are two things given. Again, Stephens law, which we have already studied, we will use that temperature. So chamber is given as 100. So I will write the surrounding temperature and I will write this as T equal to 110. 110 plus 273 will be So this will be, sorry, 110 plus 273. Yeah, to convert it in Kelvin, you add 273. This will be 383 Kelvin. This will be 383 Kelvin. Okay. So when you convert this, when you write this, so Q by T, actually the formula which we have, and rewrite the formula. We have radiant power, right? We have written the formula. Radiant power, sigma is given to you, so use this sigma value. Sigma equal to 5.67 into 10 raised to minus 8. Some SI units are given. R equal to sigma T raised to 4 minus T naught raised to 4. And as I told you, R is Q upon AT, right? So I will use that here. And from here, I will write Q upon T equal to A will go in the numerator, A sigma T raised to 4 minus T naught raised to 4. What will be the area? The shape already mentioned in the question is sphere. So area of the sphere. Area of sphere is 4 pi r square equal to 4 pi r square. That's why radius was given into sigma T raised to 4 minus T naught raised to 4. So Q by T will be equal to 4 into 3.14 into r square, that is 2.5 into 10 raised to minus 2 square into 5.67 into 10 raised to minus 8 into 383 raised to 4 minus 373 raised to 4. So you will have to solve a bit lengthy calculation, I know, but we will have to do this, and the answer will be 0.96 here. Watt will be the unit, 0.96 watt. So last question for the chapter, find the temperature of a black body if its spectrum as a peak. There are three values given. Lambda max at 700 nanometer. Lambda max is given at, you are supposed to find the temperature in each case, right? Lambda max is 700 nanometer. So convert nanometer, 700 into 10 to the power minus 9 meter. Second case, they have given lambda max is 3 centimeter. Lambda max for the second case is 3 centimeter. Convert centimeter, 3 into 10 raised to minus 2. In the third case, they have been given lambda max equal to 3 meters. Take B value as 2.897, 10 raised to minus. So we know that, see, Wien's value is given means Wien's formula, B by T. In each case, you are supposed to find the temperature. So temperature will be B upon lambda max. So for first, you will solve for first value, substitute the first value, and you will get one answer. So the answers I'm writing it. So when you first substitute lambda max as 700, the first answer which you get is 4138 Kelvin. When you put the second value, and solve again, you get 0.0966 Kelvin. When you put the third value, that is this 3 meter, and solve, you get 0.966 into 10 raised to minus 3 Kelvin. So it is just a simple calculative work. I hope you can do it. So just substitute the value of B and lambda, you will get your final answer. So this was for our kinetic theory of gases and radiation.